Hi, everyone. Welcome to Physics 151, lecture number 27. This is the third and final lecture in the series of three about rotation, which covers chapters 9 and 10 of our textbook. In this lecture, we'll cover the remaining sections of chapter 10. Specifically, we'll discuss what angular momentum is. We'll discuss the law of conservation of angular momentum. And then finally, briefly, the vector nature of rotational quantities, how twisting quantities can be expressed as vectors. I'll show three problems from tutorial number 27 as worked examples. And of course, all of this relates to online homework 27 in Mastering Physics. So first, let's define what we mean by angular momentum, again, like we have with the last couple of lectures, by way of analogy. So we already know that for translational or linear motion, we have a quantity called regular momentum, which sometimes I'll call linear momentum now to distinguish it from angular. And it's equal to the mass of an object times the velocity of an object. So if we ask ourselves, what are the analogous rotational quantities for mass and velocity? We know that those are moment of inertia in place of mass and angular velocity in place of regular velocity. So if we take the product of those two quantities, we have an analogous quantity for momentum, and we call it angular momentum, and we use a capital L to denote it. The units, the MKS units for angular momentum are just the units of moment of inertia times the units of angular speed. So it's kilograms meters squared divided by seconds. There's no special name for this compound unit or anything like that. Also note that momentum and velocity are both vector quantities, and mass is always a positive scalar with no sense of direction. So that means that momentum and velocity always point in the same direction. Well, the same thing is sort of true for angular momentum. Angular velocity can be clockwise or counterclockwise. Moment of inertia has no sense of direction to it. So it doesn't have a clockwise or counterclockwise sense. So therefore, angular momentum has to be in the same direction as angular speed, or angular velocity, I should say, either clockwise or counterclockwise. So sort of the way it's shown here in this picture here. You'll also remember that when we took our equation for impulse, we rearranged it. We were able to write an alternate form of Newton's second law that says if there is a net force acting on an object, then that object's linear momentum will change over time. Again, force becomes torque for rotational quantities, and then momentum over time becomes angular momentum over time. And we get this form of Newton's second law for rotational systems. Specifically, if an object that can rotate has a net torque acting on it, then its angular momentum will change over time. So for most objects whose moment of inertia is fixed, like this airplane propeller, that means that it will speed up, it'll spin up or spin down over time, depending on the direction of this net torque. There are some objects that can change their moment of inertia, like a spinning ice skater, and we'll discuss that sort of example coming up shortly. Let's consider what the formula for L becomes for one special case, and that is the example of a small point-like mass that is tracing out uniform circular motion. So starting with our definition of angular momentum here, L is equal to I omega. We know that for a small point-like mass that is tracing out a circle of radius r, its moment of inertia is m times r squared. We know that from before. And then we also know that the relationship between linear velocity and angular velocity for a small point on a rotating object or for a small object in uniform circular motion is v is equal to omega times r. So omega is equal to v over r. If we plug that in here for omega and simplify, we get that the angular momentum of a small point-like mass traveling in a circle about a circle of radius r about a rotational axis here is equal to mrv, sometimes written mvr. That's an expression that you're likely to see in other study guides and other textbooks. Now, this is sort of for the special case of uniform circular motion. It is often the case that we will have just a small point-like mass traveling at some velocity v in some random direction, and it will be passing within distance r away from a rotation axis. And in that case, the more general expression, right? So not for necessarily uniform circular motion, but for just any particle with any velocity v while it's at distance r from a spin axis, that angular momentum at that instant is mrv times sine of the angle between the direction of r and the direction of v at that moment. However, you won't need to use this expression for any of the problems that we're going to do this semester in Physics 151. I just wanted you to know that this more general expression does exist. All right, let's move on to the law of conservation of angular momentum. So you will recall that for linear momentum, we had a conservation law that resulted ultimately from Newton's third law of motion. And it said that the total momentum, linear momentum of a system must remain constant when there is zero net external force acting on the system. Well, in this case, again, by analogy, we're just going to replace linear momentum by angular momentum and force by torque. And we get a similar expression, which we call the law of conservation of angular momentum. Now, this is our third great conservation law: conservation of energy, conservation of linear momentum, and conservation of angular momentum. And that's it. Those are what we sometimes call the three great conservation laws of mechanics. I mean, once in a while, there's other times here and there when we say a certain quantity is conserved, just to mean that it's constant. But these are considered, for systems in general, these are considered the three great physical quantities these are related to deep behaviors of nature, like Newton's third law. All right. To write this out formally, we remember before we did it with P total equals P1 plus P2 plus P3. We can do the same thing with L. Formally, it's actually a vector equation for reasons that I'll get to at the very end of this lecture. So if we write these out as L vectors, then we get an expression that says this: the total angular momentum of all the pieces within a system at any earlier time before they interact with each other will be the same as at any later time after they interact with each other, assuming there's no net external torque from the outside. Now, there's sort of two ways that we tend to use this with our physics problems. One is we sometimes have problems where two or more rotating bodies, or bodies that could rotate, are all aligned along the same rotation axis. So all of them have their sort of spin axes aligned with each other, and then they can interact with each other. And I'll discuss a couple of examples coming up. In that case, we write the expression out like this, and we're just going to, instead of writing out the full vectors, we're just going to consider the clockwise or counterclockwise. In other words, negative or positive components for each of these L quantities for each of the pieces that we're concerned with. And usually for our problems, it'll just be two pieces. And then the other way that we use this is when there's just only a single object. And in that case, it will be something like a spinning ice skater that can actually modify its own moment of inertia. So in that case, we just have L1 initial and L1 final. It's just a single body, but that body is not fixed in its distribution of mass. So it can change its moment of inertia by changing its mass distribution. And then we just get that L initial equals L final. So let's consider these two in reverse. Let's talk about this spinning ice skater case first. So in this particular case, what we have is we have an ice skater who can change their moment of inertia by pushing their mass distribution far from the spin axis. And at those moments, their moment of inertia gets large. And then at later times, they can pull their mass closer to the spin axis and their moment of inertia gets small. And they can go back and forth between those two, as we see in these spins. So here, large moment of inertia, now that smaller moment of inertia, this sort of an intermediate value, and now a very small moment of inertia. And you can see how the spin rate varies in inverse proportion. And then at the very end, she sticks her body her legs and arms and her limbs outward again. And at the very end, she slows down again. Ice skaters even do this when they're jumping. They start with their arms and legs out really far, and then they quickly tuck into a tight body configuration. So that way they can spin quickly in the jump. And then as they come out of the jump, they extend their arms and legs once more, and that slows down their rotation right away. So what we can do is say L of the skater at any earlier time is equal to L of the skater at any later time. We can define initial and final this way, or we can define initial and final that way. Whatever, it doesn't matter as long as we make the assumption that air drag and other forms of friction and other things, frictional torques and other outside torques are negligibly small during the time period. And what we find is writing out L as I times omega. We have I initial, omega initial, and I final, omega final, where now the moment of inertia will be different in each case, as well as the spin rate in each case. So this is one of the sample problems that I'll show. This question number 4 is an ice skater-like problem, and I'll show how to use this formula in that case. This is the other situation that I mentioned, where you have 2 or sometimes more, but usually just 2 interacting bodies who share a common rotation axis. And in this case, sometimes there might be a collision between the 2 bodies. So let's say the 2 bodies are initially spinning at different rates, and then they come together and they have an interaction with each other where they hook together or they slide against each other frictionally until they come to some common final speed. So this is a lot like the collision between 2 moving carts moving along the x-axis that then collide and stick together, and then they have some final velocity together afterward. So it's sort of analogous to that situation. And in that case, this would be the 2 disks before they interact with each other or collide. And then this would be the 2 disks after they collide. But if they are stuck together indeed, then both of these 2 omegas just become omega final. But I don't need to distinguish omega 1 from omega 2. And the 2 moments of inertia just add. Another example is that of sort of a gunshot where you have a recoil. So here, well, let's talk about the rotating case first. The blades on the top of the helicopter and the body of the helicopter share a common rotation axis right here. Everything can, let's say, start from rest, hypothetically, and then if the motor blades start to, the blades on the top of the helicopter start to spin clockwise, what will happen is the body of the helicopter, if it's not touching the ground, if it's free to rotate, will automatically start to rotate counterclockwise as a sort of recoil. And it's due to the fact that, whatever motor or anything that is operating right here at this joint will always exert an equal and opposite torque on the other body due to Newton's third law. So whatever torque is causing the blades to spin up clockwise there will be an equal and opposite torque anti-clockwise on the fuselage. Now the fuselage has a much bigger moment of inertia. So as a result, it will gain a much smaller amount of angular speed, but nonetheless, it will start to rotate in the opposite direction. That's sort of a recoil, just like a bullet being fired from a gun. Everything might start at rest. The bullet leaves at a very high speed in one direction, and the gun, whose mass is much larger, will recoil at a much lower speed in the opposite direction. By the way, this is why helicopters have these little tail rotors to try and help prevent the rotation of the fuselage. Finally, I wanted to mention that this shows up in natural systems over and over and over again. Now, in natural systems, we have many, many tiny small pieces of mass in either this liquid water here or the gas of the atmosphere for this hurricane, or the tiny pieces of gas and dust or molecules of gas or little tiny pieces of dust in. This is a protoplanetary disk orbiting around a very young or protostar right here. And what happens in all of these systems is due to interactions of the matter with each other. Well, first of all, in all these systems, there's often some sort of a force that is trying to pull the matter toward the center. So in the case of the vortex, the water vortex going down the drain, of course, it's gravity pulling the water to the center. In the hurricane, it's low pressure pulling the gas toward the center. And in the case of this protoplanetary disk, it's gravity trying to just pull the gas and dust toward this center right here. Um, but what happens is if there were no rotation at all to the system by some amazing miracle, which is incredibly unlikely, then it's true. All of the molecules would just sort of head straight toward the center. They crowd together and eventually collide gravitationally or go down the drain or collide here, under pressure. Um, but what happens is in all these systems, there always is some minuscule amount of random net rotation in the case of the vortex, the water vortex, or the protostellar system. Or in the case of the Earth with hurricanes, it's due to the Coriolis effect, which creates a very small differential rotation between the north and southern edges of any parcel of air. So as a result of that, each of the little parcels of mass in any of these fluid systems here or this orbiting system here has some initial angular momentum about the center of the system. And as any one of those parcels migrates inward, then either if it's not colliding much, it will try to conserve its angular momentum. And the only way it can do that is as its moment of inertia decreases by getting closer to the axis of rotation, it has to increase its angular speed and therefore its linear speed. So its speed will go up as its radial distance from the center goes down. Another thing that happens occasionally is little interactions where in order for, when collisions are a lot less frequent, like happens in these planetary systems, then in order for a little chunk of mass to head inward, it has to have some sort of close call or collision with another chunk and send that chunk outward. So that's one way that little chunks get ejected. Some chunks get ejected as other chunks fall in. And these jets here are thought to be one way that nature ejects a small amount of mass at high speed in order to allow more mass to fall in at low speed. So in all these cases, we see this we see this increase, of speed as you get closer and closer to the center. So this is different than a rigid body, right? When we have a rigid rotating object, then in fact, the opposite happens where the linear speed increases toward the edge because the whole thing spins at one angular speed or one angular speed like this. However, here, the different pieces can rotate about the center at different speeds. But the reason that they have to increase their omega as they head inward is because they've decreased individually, these parcels of mass have decreased their moment of inertia I. So over and over again in nature, we keep seeing this sort of vortex form, right, where we have increasing speed toward the center. I also want to point out that the moment of inertia of the system does not change if the mass moves parallel to or along the spin axis. So as a result, as a result, gravity, this might have started out as a spherical cloud of gas in all directions, or this galaxy over here might have started out as a spherical cloud of gas. Gravity will try and pull every little piece of matter toward the center. And what will happen is matter can fall parallel to the rotation axis without changing the moment of inertia of the system. So it can freely fall along the rotation axis and it doesn't have to go any faster as a result. Instead, though, if it tries to fall toward the spin axis in this direction or that direction or this direction or that direction, that's where it has to pick up a lot of speed very quickly in order to conserve angular momentum. And that's hard to do, right? That requires a lot of energy. So as a result, billions of years have passed here and all of this gas turned into stars and now they're all happily orbiting before the gas could finish its collapse toward the spin axis here. And the same thing happens. So much time passes that planets are able to form from this gas and dust instead of all of it just simply falling inward. But this disc shape, this pancake disc shape, we see over and over again in nature. Let me conclude here by briefly touching on something that's at the end of this chapter, and that is the fact that we have this mathematical tool where we express these twisting quantities, right? Like omega, angular velocity, angular acceleration, torque. These are all things that when we look along the rotation axis can appear to be clockwise or counterclockwise. So up until now, I've always sketched these as little curved arrows. However, mathematically, we can come up with a convention that allows us to express each of these as a straight arrow vector, just a standard straight vector that lies along the rotation axis. And this lets us do vector math, vector operations, vector mathematics with these quantities that we couldn't do when they were being expressed as these sort of curved arrows. So here's the convention we use. Here's the rule. First of all, if a particular rotational quantity like torque or angular velocity is in either a counterclockwise or clockwise direction around an axis, then we're going to create a vector that lies along the axis. So you can see here's a torque vector right here. There's a angular momentum vector. Angular momentum vector or angular velocity vector. But we need a rule to tell us which direction to point that vector. Should it point up or down? Should it point up or down? Or in this case here, should it point to the right or to the left? So the rule we use is use your right hand to let your right hand fingers naturally curl in the direction of the curling rotational quantity. So notice how this person's right hand fingers are just naturally curling in the same direction that the torque is being applied to the screw. Or here, naturally curling in the direction that this angular speed is going. Look at the direction your right thumb is pointing, and that right thumb will point in the one of the two directions along the axis that you should then draw your vector. Okay, we only have to choose, up or down on the axis, or in this case here, it's right or left. That's it. So your right hand thumb will point in the proper direction to draw the vector. So here you can see the same thing. If, as we look down from above, this merry-go-round is turning counterclockwise, or has a torque applied to it, I should say, that's counterclockwise, then the torque vector should be drawn upwards. See this person's right hand, fingers curled, thumb up, then we should draw the torque vector upward. Remember that angular momentum and angular velocity always point in the same direction. So if you know one of those, you immediately know the other one. All right, with that, I'm going to end the video, this portion of lecture 27, just to keep the videos a little shorter in length. And when I resume with the next part of the video, I'm going to solve 3 of the problems on this particular tutorial set as sample problems.